So what is the difference between filtering and estimation? How do they really relate to each other? If you think of filtering as the process of removing unwanted components from a signal and keeping some kind of wanted components of the signal. Typically, the unwanted component is the noise, but it may be something else as well, right? So it may be that you want to filter out, let's say you have a fence that you're taking a picture from, and you want to filter out the part which is part of the fence, remove it from the scene. That would be an example of filtering. A couple of examples here, low pass, high pass, band pass filters. We talked about this maybe in your signal processing. Yeah, we'll go through them quickly, but I expect that you know all about this. And then there are more complicated filters, like Kalman filters. Did you do Kalman filters at some point? Well, we will talk about Kalman filters actually more next time when we talk about estimation, because Kalman filters are also estimated, or they can be used for estimation. So estimation in this case is more about inferring the state of a system, right? Or inferring the state of some kind of variable that you're interested in, estimating it from noisy measurements. So they kind of relate these two concepts, right? In one case, you're filtering a signal. In the other case, you're using the signal to estimate the value of something. So a typical example here in robotics would be estimating the pose of the robot relative to a reference frame. And we're going to actually use this example throughout when we talk about estimation, and we'll pose it a couple of different ways that we can do this. Kalman filters is one of the ways that we can do this. Particle filter is another example. And then we'll talk a little bit about maximum likelihood estimation and expectation optimization, how it works. Yeah, so filtering is more about processing signals. Estimation is more about estimating parameters. And today we are going to talk about filtering. We'll cover some typical filters in signal processing. Then we'll talk about, in particular, removing noise from images or filtering images, and then a little bit about how we can filter 3D data. Okay, so if we go back to the definition that we had in the first lecture, I think we said that we have a signal Y, and that is based on some ground truth kind of process X that's generating the signal. And then we have two different kinds of noise that are added on top of it, systematic and non-systematic noise. And we said that the systematic noise is obviously what we want to remove through calibration. So the non-systematic noise is something that we need to filter out in another way. So how do we filter out this noise? So here's an example of a signal which has, I think actually the other way around. The green one is the original signal, and the blue one is the filtered signal. So we have had some signal that was corrupted by noise. We know something about the process, or we suspect something about the process, and we try to estimate this kind of smoothed signal, which doesn't have noise. This and in signal processing is called the Fourier transform. And here I expect you remember Fourier transforms, right? Okay, so it's a standard way of thinking about signals. Instead of thinking about them in the time domain, I think about them in the frequency domain. So every signal can be considered as a superposition of different frequencies, right, of sine waves. And then instead of looking at the amplitude of the signal in the time domain, or how the signal changes over time, we say, well, this is just going to be represented as a spectrum of different sine wave frequencies that are added on top of each other. And these are the definitions. So the continuous space definitions for for a signal here, it is this ugly looking integral. And then if we take the Fourier or the frequency domain signal, we could use the same kind of ugly looking integral to go back to the time domain. And this is something that you are aware of, right? You can switch between signals in time domain and spectral. Why is it interesting in the context of filter? Well, obviously because we have kind of an idea here that the noise is going to be different from the signal, and is going to be different, especially in the frequency domain. So typically, if we take the original signal here that we looked at, and we take the amplitude of the spectrum, we'll notice that, okay, there are a couple of components here. So this is the steady state, right? So that's how far up from the zero the mean of the signal is, right? That's the frequency component of zero. But then you'll notice there's a strong frequency component here at around 50, and another one at 120, something like this. And the rest is actually noise, right? So if we knew that, then we could easily design a filter here, frequency domain, to filter out all of these noise frequencies, but only pass through this signal frequency. Well, the problem is that we don't typically know what the correct frequencies are. However, there is a general truth about signals is that the noise is typically the high frequency components of the signal. So one way to filter out noise, and we're going to look at that, is just removing the high frequency components. But another thing to think about here is convolution, and that's one of the few things that I remember from my own personal time when I took the signal processing courses was about what convolution is, right, and why it matters, and also how convolution relates to Fourier transform. I don't know if you remember how the convolution relates to the Fourier transform. No? I think that's the one thing that you should remember from that. Well, first let's talk about what is convolution. So you can think of filtering as taking the signal, the original signal, and convolving it with the filtering kernel. Right? The filtering kernel, in this case, is a Gaussian, in our case, right? So we're going to say, what we're trying to do is we're trying to smooth the signal by taking every point of the signal and substituting it with the multiplication of this signal and the full signal, right? And I'm going to do that at every point in time as I move along. And that's the convolution essentially operation. Yeah.
Is this like a moving average? Or?
In this case, it would be a moving average, but a kind of a weighted moving average, right? It's weighted by this Gaussian signal. If you had a step here, that would be indeed a moving average. But we can have different filtering kernels. And a lot of the talk about how we filter stuff is designing this kernel, designing what this kernel should look like. And we're going to see that this same concept applies to images. So when we filter images in some way, we're convolving them with the filtering kernel. Okay, but from a mathematical point of view, you write this out like that. So this is saying if we have a filter kernel, that's G of t, that's the red thing here. And if we have f of t, which is the signal, we can compute the filter signal, the convolve signal by this convolution operation. And this just tells you what I just said. You take the integral. So at any point z, the integral is f of t times g of t, so multiplying the two signals together. And here you have to vary, of course, the variables correct. Okay, and That's what we get, right? We move along. So why is convolution related to Fourier transform? It is the so-called convolution theorem. As I said, this is the only thing that I remember. So given these two signals, f of t and g of t, and if we take the Fourier transforms here, capital F of omega and capital G omega, then the convolution theorem states the following: the convolution of f and g is the inverse Fourier transform of the two Fourier transforms multiplied by, right? So why does this matter? It matters because if you wanted to calculate this integral here, in reality, for two given signals, analytically, this would be very difficult for random signals, right? This filtering kernel here could be anything. If it is a Gaussian, maybe it is possible to do this analytically, but it could be very different kinds of kernels. So calculating this integral is not something you want to do. Calculating the Fourier transforms is something that we can do very efficiently, right? We have algorithms to do that for us. So we can do FFT, like fast Fourier transforms. So calculating these Fourier transforms is very fast. Calculating the inverse Fourier transforms is also very fast operation. So my signal processing professor was always saying, if you want to do a convolution, you just go to the Fourier domain and you multiply. That's it, right? So in signal processing, this is a common way to filter. Instead of doing filtering in the time domain, you take the frequency domain version of the signal and you multiply then with the filter in the frequency domain and just take the Fourier transform back. Yes, this is what I said essentially, that we can do that really quickly, and it simplifies a lot the process of filtering. So with this in mind, we can then take a look at the low-pass filter. So low-pass filter is motivated from circuit technology, right? It is like taking a signal that you have here over the input signal, passing it through this RC circuit, right, where you have a resistor and a capacitor, and measuring the output over the capacitor. What does that do? That essentially smooths out peaks, right? It smooths out peaks because the capacitor there takes time to charge and discharge. So the central idea here is let through the low frequency components and dampen the high frequency components. In frequency domain, you can think of this filter kernel as looking more or less like this. All right? This is the ideal low-pass filter. You have a certain range here up until this frequency here, the band, right? And in that range, the filter is passing sequences through. And from here on, it is the stop band, so we have 0. And this is the frequency domain representation of the filter, right? This is not the time domain representation. So we take the frequency domain version of the signal and we multiply it with this, then we would get the filtered signal. Okay, so what does it do? It smooths out peaks, right? So we take the original signal, we pass it through a low pass. We're going to have this kind of smoother and slower varying signal. Related to these are the high pass and the band pass filters. Right? High pass filter will be the inverse of a low pass filter, so that means we would only pass through high frequency domains, high frequency components. It's equivalent to taking the output over the R in the RC circuit that we just saw. And why would you want to do that? In reality, well, you wouldn't want to do it if you want to remove noise, obviously. But there are some applications. So you can think of, for example, detecting edges in images, right? This is the place where there is a lot of switch in frequencies. This is the place where the high frequency components are important. Texture. If you want to extract that, then maybe this is what you want to do. In frequency domain is kind of the reverse of processors. Now, why do I talk about sloping here? A ramp function. What I showed you there was not a ramp function, right? This was a step function. It's because when we do this is the ideal version of the filter, right? If we implemented that filter in reality on a real RC circuit, then the real representation would not be a sharp step. It's going to be kind of a sloping ramp. Okay, and the band pass filter, right? If we can combine the low pass and the high pass filter, then we can say we are only passing through a particular frequency band, right? So a band pass filter would be, look at the magnitude, right? To be a certain area where we're passing through the signal. And this is in cases when we have some prior knowledge about the place where we are looking for a signal. So many of the sensors we looked at before, they will do this kind of signal processing inside in order to analyze the raw measurements that they're making, let's say, on the pixels or on the velocity of the voltage drop over certain resistance or something like this. They're calculating levels of potential drop. Okay, so this is a theory, and you should be aware of all this already from your signal processing. But for us here, we often deal with discrete time systems, right? So what does that mean for us? If I ask you, okay, there's this signal that you saw over there, implement a low pass filter, what would you do? So you don't have access to the full filter, the full signal the whole time, right? You need to produce this filtered output typically on the fly as the signal is coming in. You cannot just capture signal for a long time, calculate that fee, do all these things that we talked about. In these cases, you might want to do a discrete time approximation of these filters. And sliding window filter is a simple approximation. And if we kind of restrict the size of this kernel that we're sliding, then we can implement some of these filters in a kind of easy way. So, for example, this is the discrete time approximation for a low pass filter. That's a filter that you might want to use sometimes in your code. I've used it quite often. So what do we do? As we're producing the final output signal here, and you can do that on the fly. You're just keeping track of the previous value of the filtered signal. All right, so this is the value at the previous time step. You get a new measurement here, and you mix them like that. Right? You take alpha times the new measurement, and then 1 minus alpha times the old measurement. And if you set alpha to something really high, what's going to happen here? Well, first of all, alpha is between 0 and 1, right? Clearly, yeah. It has to be a value between 0 and 1. If we set alpha to 0, what happens?
Then the second part is going to be 0. Close to a very small.
No, sorry, alpha to 0 would set the first part to 0, right? Because yeah, here. And the first part is the actual new signal, so it's going to be a completely flat line, right? The signal is never going to change if alpha is 0. Right? If we set alpha to 1, then we just pass through the signal without performing any filter. Now, if you set alpha to something close to 1 but not 1, like 0.95, for example, then you would be passing through a large part of the new signal, but smoothing it out with the previous value, right? So you're kind of making the signal change a little bit smoother, right? And this is, in effect, what a low-pass filter does as well. So here's an example of low-pass filter, discrete time low-pass filter on that signal, previous one. The blue is the actual true signal that we're trying to reconstruct from the previous noisy signal that we saw before. And alpha 04 and 08 here are two examples of two filter signals, right? So you can see the higher alpha passes through more of the noise. Right? The red signal is more noisy. And the lower alpha here smooths things out more, right? But it also smooths out parts of the signal. And obviously, this is not going to reconstruct you the real true signal because it's an approximation. Okay, so the next topic we're going to cover is images and noise in images. So here is the Mandrake picture that you remember from before. Here is some noise added on top of it. So what kind of noise should we expect in an image? There are different sources and different types of noise that you can get. Some of it is very difficult to remove. Some of it is possible to process away relatively easily. So typically we distinguish about this kind of three different main categories of noise. There's the, well, I'm talking about non-systematic noise. So systematic noise we talked about before when we talked about vibration, right? These were the distortions or the motion blur or rolling shutter effects, right? These are the systematic noises, but what about the non-systematic noise? The one that kind of comes in randomly and is difficult to remove with some model. So we can think about three different kinds. So additive Gaussian noise, that means per pixel you would get added some amount of Gaussian noise that changes the value up or down a little bit. Then there is salt and pepper noise. This is an example over here. You can think of it as kind of dead pixels. There is a dead pixel somewhere on the camera that just goes blank, or it gets a shot of white. Right, so this is an example of salt and pepper noise. There are speckles that kind of appear around the image, but they're randomly appearing and don't know where. And then there is something called multiplicative shot noise. So this is noise that comes in where the noise is kind of multiplied to the signal. It's not an addition of some small noise component, but the noise itself depends on the magnitude of the signal. And that, for example, could be like similar to the pixel blooming that we talked about before. And this is noise that is quite difficult to model and to get rid of. So to remove these types of noise, it is often common to post-process the images in some way. And the most typical way of doing that is by convolving them with a filter kernel. So this is again the same idea as what we talked before. We have a kernel that is then for a mask. It is passing through the image and is sliding through the image and it's calculating the new values of the new image by taking the pixels that are under this mask and multiplying them with some value. So here's an example of one kind of filter kernel that you could pass through, which takes the current pixel underneath, right? Multiplies by half, and then every other pixel around gets a value of 0.05 times the value that is there. You add this up together, And then this is the new value of the pixel. And there are different kinds of filter kernels we can pass, and we will talk about 3, I think, of these kinds of filter kernels and what they're useful for. Now, this is a general setup, so it's not only about filtering out noise. It is the most common way of using these types of kernels to detect signals as well. So maybe what we want to do is we want to detect all the edges in an image, do something with it. Convolving with a filter kernel like this is a common way to do that. And the size of the filter kernel can also change. Typically, it is an odd number because we have the central pixel, and we want to have a central pixel. So it's usually either 3 by 3, 5 by 5, 7 by 7. So filter can grow in size. And you will talk about this kind of image filters and what they're useful for when you take your image processing course later on next year, I think. But there are a couple of things you should take care of when you're convolving an image, this kind of discrete convolution of an image with a filter kernel. So one of the most typical problems is how do you deal with the borders. So think about this picture that we had before. I started from aligning the kernel like this, but in practice, what's going to happen now is that when I multiply these things, I'm going to get a smaller image, right? This pixel here, the first one is overlapped. So how do I deal with this first pixel? Right? How am I going to produce a value for the image in this place? And if my kernel size is 9 by 9, that means I'm not going to lose just one pixel, I'm going to lose 4 pixels around the border if I start from here. So there are different ways that you could deal with the border of the image. You could shrink the image size, right, by half the kernel size. That's what we said. So what we're doing here, essentially, we're dropping the border pixels and the image is smaller, the filtered image is smaller. But you could also do other things. You could, for example, pad here with zeros. You can say everything that's outside here, it's a 0. So I will just pad here with zeros, and I'm still going to produce value. Obviously, that's kind of going to affect the value around the border side. We're going to get darker values here because they're multiplying by something which is black outside. So it's like extending the image with a black border around. You could extend the image with a white border around it as well. But again, this is polluting the image signal. And then you could also kind of pad it with copies of the border pixel, right? So you could take this pixel and copy it out here, like here, right? So this is a little bit less intrusive. In the end, probably shrinking the images. It's a common way of doing this, and we can live with it with the sizes of today's image arrays. So let's cover a couple of these filters. The first one is known as the mean filter or the average filter, and that is the sliding average that you suggested previously when we talked about signals, right? So the weight for every element in the weight average, in the sliding average will be 1 divided by Ni times Nj. Ni and Nj are the horizontal and vertical sides of the kernel. Typically, this is square, right? So that will be 1 divided by n squared. Why is that? Well, because we want that all of the weights, when you sum them up, reach 1, right? We want to do that because we don't want to change the overall magnitude of the image. If the weights sum up to something higher than 1, the image is going to become lighter than the origin. If they sum up to something lower than 1, the image is going to become darker than the origin. So here's an example I ran on the original noised up membrane image. Mean filters of different sizes of kernels. Right? 3 by 3, 5 by 5, and 9 by 9. So what can we notice? A little bit small, the images from here, so you don't see it too well, but there is still a little bit of a sign of the salt and pepper noise on the first image. I don't think you can notice where the salt and pepper pixels were on, for sure not on the 5x5 and 9x9 image. But of course, when we go higher up, you notice how quickly the image blurs, the details disappear. And not only this, we also get this kind of axis aligned streaks, and this is because higher value pixels kind of start dominating and bleeding into the axis around. So if you would repeat running this filter a couple of times, you would notice that this starts becoming quite pixelated and the pixels are aligning with the axis. All right, so nothing super spectacular about the mean filter. The next filter that we look at is the Gaussian filter, and that's another common way of smoothing out noise, of removing noise. Instead of using flat, square, weights, we're going to use the Gaussian distribution to calculate this filter kernel. And you remember what the Gaussian distribution looks like. It's this little fellow over here. You can calculate it in 2 dimensions. Say we have a 2-dimensional variable, which is the ij location of the pixel. We have a mean. The mean is going to be in the middle, right? So this is a, I think, 13 by 13 filter size here. So it's a big one just for demonstration. Right. So the mean here is at when the value is in the middle. I think in this case, this particular Gaussian doesn't have a mean. So add it, but then the further away you go from the middle, you get lower and lower values of the kernel. And it is a symmetrical Gaussian kernel, so that means it's like a circle, right? So the Gaussian spread equally on all directions. What is the advantage of doing that? The advantage is, of course, that pixels which are closer contribute more to the result than pixels which are further away. Pixels, sorry, not pictures. So here's an example. Again, 3 by 3. Oh no, these are 3 different 9 by 9 kernel sizes. And what we have varied here is that we have varied the variance S. So the standard deviation of the kernel size. So we could vary 2 things here. We could vary the kernel size. We could vary the standard deviation. If we have a large standard deviation, then we mix signals from far away. If we have a small standard deviation here, half a pixel, it means that we keep more or less only the central pixel and you can still see the salt and pepper noise. Okay, so this is what's Gaussian blur. If you have an image processing program at home and you open an image, you can easily apply a Gaussian blur and see what the result looks like. So a little bit better than the mean filter, but still not ideal because it blurs out a lot of the details. Now, there is a filter here that we're going to look at that's not really a linear filter like the ones that we've seen. So previous filters that we looked at, they were all linear filters in the sense that when you calculate the output, it is a linear function of the kernel and the signal. The median filter is a nonlinear filter in the sense that the function that we get out is a nonlinear function. So it still depends on the value of the kernel and the value of the signal at this particular location, but it's not a linear relationship anymore. So what we do is instead of calculating sums of line things, we're going to look at the window underneath the pixel, underneath the filter. Let's say 3 by 3 here, right? So we're sliding this filter around the image, and then we look at all of the pixels that are inside the window. All right. Okay, 9, so 9 pixels here, and what we're going to do is we're going to sort them. We're going to sort them by the value, right? By the intensity value here, and that produces some sequence, like I don't know, 7, 5, 8, you know, okay. And the median filter will select the median of this sorted sequence and substitute the value in that median value. The median value here means, you know, the one that is in the middle of the sorted. Yeah. Right. Remember when we talked about RGB at some point? I told you we're going to see why it is a good idea to transfer things into HSV space. All right. That's what you do if you want to do a median filter on an RGB image. You transfer it to HSV space, Q saturation value, right? And you do the median on the value. So you can select pixels based on the value in the V image. And say, okay, this is pixel 7 is the median pixel. Then I can substitute both the HS and the V of the new image with the HS and the V of pixel 7. You could also do it by calculating the the average of the pixels, right? RG and V, the average of the pixels, and solve based on that. But HSV is a typical way. So here's an example: median filter, same image, 3 by 3, 5 by 5, 9 by 9. We definitely notice a lot of artifacts. The higher that this goes, right? So it kind of becomes a little bit cartoonish, right? Because the texture disappears from the image. And that's normal, right? Because the texture is the high frequency component. But if you have a smaller size, then all of this single pixel kind of salt and pepper noise that we had is gone already at the 3 by 3 size. Yeah. At least I think it's gone. Yeah. Okay, so these are 3 typical examples of filters, 3 common ones that we use quite often for filtering noise. I wanted to give you a couple of other examples which are a bit more interesting, examples that we don't use that often, but I think are nice filters to know about. Bilateral filter, for example, is a filter that you could use for this task exactly, and it is a filter that is smoothing while preserving edges, right? So it's an edge preserving smoothing filter, which is quite nice, right? This is what we want. We want a filter that smooths out the signal, but keeps the edges, right? Smooths out the noise, but keeps out the signal, the edges. And the main idea here is that you would calculate the filter kernel based on the values of the pixels, right? So instead of having a fixed kernel, we're going to have a kernel which changes based on the intensity of each pixel. So what a bilateral filter does is that it calculates 2 Gaussian kernels. One in spatial domain, so based on how close you are to the center of the filter, and one in pixel intensity domain. So that means how close your pixel here is to the intensity of the center of it. And it gets formulated like this. So these are the 2 different, right? 2 Gaussians, and what happens? What happens when you multiply 2 Gaussians? Well, you get a new Gaussian, right? So this is 2 Gaussians actually here, right? E, and this is the first Gaussian, and this is the second Gaussian. And the first Gaussian here is what we saw before, right? This is based on the proximity, the coordinates ij of the filter pixel. And the second Gaussian here is based on the intensity. So capital IW here is the intensity of the central pixel. And intensity here of ij is the intensity of the pixel from the image under this current, wherever the filter kernel currently is, you calculate at this point in the image what is the value of the intensity. And we have two sigmas here, right? One based on the distance, so how far to spread, and one based on the distance in intensity space. And then we have a normalizing factor, which is going to be recalculated depending on the current sum of all of these pixels, right? Because it needs to normalize to 1. Okay, this is what I mentioned. So how does this actually look like, right? So this is a little bit abstract maybe. Here is an example. So all lectures by one the professors was around here, but I think it's a really good visualization, so I always steal it. Here's some input image over there, and this is the actual image patch, you see? And this will be the bilateral filter kernel in each of these places. So over here, where there is very little texture, we are reverting to the typical Gaussian blur, right? So we have the same kind of Gaussian blur, Gaussian kernel. And why is that? Because the intensity difference between pixels here and here is essentially 0, right? So that means that the second Gaussian is we're very close to the mean of the second Gaussian, so it's not going to change the kernel. But if you look over here where we have the edge, right? If you look the image patch over there, it is kind of black on one side and light on the other side. And this is what the kernel is going to look like. On this side, we are looking more or less like we did before, a flat Gaussian, but the intensity difference between pixels on this side and the central pixel are very high, right? This is a very high intensity difference. So what does that mean? That means that probably we shouldn't be using the values of those pixels to calculate the filtered value of the pixel we're currently processing, right? Because we don't want the color here of this pixel to get polluted by the dark color here of the foreground function. And that's an elegant way of doing that. And it can look quite complicated. So in places like here, where there is a lot of texture, you see that the kernel looks nothing like a Gaussian in this case, right? But in reality, it still is a sort of a Gaussian that has been, sampled by a second Gaussian in the intensity. And this is the output here of the filter image, where you see the stuff has been smoothed out, but the edges and the big signal is preserved. Here's an example with the image that we looked at before, the one in the Mandrake. In this case, we have two parameters to vary for the kernel size, right? One is the spatial kernel size, and the other one is the intensity kernel size. And maybe some of them were a little bit too low. So up here, there isn't much of a difference. But you notice that when we increase the sizes of these kernels, then we start removing more and more of the texture. This is, I think, one of these filters that they use for making cartoons, actually. So if you want to try it out, many of the image processing software these days implement a bilateral filter that you can run through an image and see what happens. I don't know, for all I know, maybe TikTok has a bilateral filter. Body. Okay. Questions? Good. Then a couple of words about how we filter 3D data. So a lot of the attention we had so far was on images, right, or on signals, which are one-dimensional signals that we want to filter. But what about all of the range data that we talked about is three-dimensional data, right? So data in 3D. Is there something special about it, about filtering noise that we get into these range sensors, for example? But to be honest, there isn't anything super specific. People do try some ways to filter noise to 3D. We're going to take a look at it. But many of the methods are just extensions of the 2D methods that we looked at before. And most of the sensors, they have already noise filtering and noise processing inbuilt in the signal processing from the sensor, as they are quite complicated sensors. For example, for stereo cameras, there are complex algorithms these days that try to estimate places where there is lack of texture, or detect whether components are connected, or in fact, these days there are even AI models that try to figure out the distances of parts of the image based on what is in the image actually. Time of flight sensors, for example, as we talked about before, they would have methods to filter measurements based on intensity, or detect the fact that this is ambiguity, right? Disambiguate measurements, right? Get rid of the ambiguity. Folding range. And these are very specific to the kind of sensor. But there are a couple of ideas that are extendable beyond that. So the first one is, for example, we can take a look at taking the depth image and just applying some depth, some of the filters that we just seen to depth image. And here we have three images. These are not exactly depth images. In fact, these are this is edge detection being run on a depth image. All right. So when you see white pixels here, these are places where there is a lot of depth texture. You can see clearly there are some objects here, right? They have kind of the boundaries around them. So these are three different filters that were run, or actually two filters on the original image. I think the original image is on the left. And these two filters here are bilateral filter and a TVL1 filter. TVL1 filter is something we didn't talk about in the image space, but it is an image space filter. It stands for total variation of L1 norm of pixels. So it's a filter that tries to reduce the variation between the L1 norms of the pixels. So you can kind of start smoothing out these images. So what you want is that you want to smooth out noise of the actual signal. This is an image from the same paper, actually, one of my ex-PhD students worked on it. And now maybe you can figure out what this was. Right? This is rotated on the side, but it is the same kind of scene where there are a bunch of barrels and boxes, containers. And this is what the original image looks like. And the image on the left is case where the image has been filtered. Well, it has been filtered by a 3D filtering method in this case. So this is not based on the bilateral filter we saw before. This is a method that integrates measurements in a 3D volumetric data structure, and then re-renders the images based on this fused volumetric filters. And how does that work? You don't want to go into the details, but it uses something called signed distance field. I don't think we have. Didn't have plans to talk about signed distance fields, but I mentioned it just so that you have an idea. A signed distance field is a simple idea. Essentially, it says imagine that you have an object here, right? And you're looking at it on a camera over here. I would like to create a kind of a 3D, or in this case, a 2D way of representing the surfaces of this object. Right? You can represent the surfaces of the object in many ways. You can represent them by looking at points which are on the surface. Say this is the surface, right? Or you could say I'm going to create a mesh here, right? That sets the surfaces of a bunch of triangles. But sine distance field is what's known as an implicit way of representing the surfaces. So instead of representing the surfaces, I'm going to say I'm going to make a grid here. Right? A regular grid of points. You can imagine the rest. And for each point here, I'm going to calculate the value. And if that point is outside of the object, I'm going to give it a positive value. And if that point is inside the object, I'm going to give it a negative value, right? And if that grid point just happens to be exactly on the surface, its value is equal to 0. Okay? So instead of representing the surface, we are representing this implicit way of representing the surface. And the values here are not just positive, but they're actually the distance between this point here and the closest object. Right? So here I'm going to give the value of 3.14 meters. Here I'm going to give a value of minus 1.5 meters. Okay. So there are methods that you can reconstruct these fields based on observations from a camera. And that's what was done here. These points were put into such a distance field. And then from the distance field, we created a new way of generating all of the surface points. And that's what we got. And in this case, there is substantial smoothing of the image. It's a little bit unfair because this uses more than one image from different directions, but you can get the idea. There are ways that you can filter data in 3D and not in a simple like 2D method. Okay, another example here of 3D filtering. I think I was planning to talk about it, but I don't know why I don't have a slide. Is subsample. So if you have points. And these points here, you could select a subsample of points by taking a 3D grid and sampling only single points. But yeah, I think there are more involved methods of filtering noise in 3D. I don't think we need to go into details. Okay, this finishes part 1 here of